Thank you very much, Geza. I will introduce myself soon, but before that, I also want to ask you to type your name and institution in the chat box as well, because we want to collect your names, the participants or the participants today. Okay, thank you very much. Let's start with the workshop. As Geza already mentioned, this is the second workshop in this series. It is for intermediate level GIS user. So I think you are already using some kind of GIS. You have some experience in this field. And I prepared this presentation based on this assumption. So first of all, I want to introduce myself shortly. My name is Zalán Tobak. I am a GIS and remote sensing specialist and working at the University of Szeged, Hungary, at the Department of Geoinformatics, Physical and Environmental Geography. I'm teaching and doing the research since more than 15 years, and these two workshops, the first one for beginners and this one for intermediate users, I will do this today. Okay, let's see the schedule and the topics for today. We will have 2 parts and the short breaks between. It's about 15 minutes. In the first part, we will talk about the data quality. It will be the main topic in this part, and the metadata. In the data quality topic, we will see the definition of the data quality, of course, and different metrics of the data quality. How can we measure, in which aspects can be used to measure the data quality, especially for spatial data, of course. And we will also see some examples in the GIS data for this data quality components. Okay, and the second topic in the first part will be the metadata. As you know, the data about the data, the instruction manual for data, So we will see the first definitions, and we will talk about the importance of metadata. I will show you some standards, most or commonly used standards like the ISO or the American FGDC standards. We will talk about some common errors connecting to metadata, and as you already know, you have a metadata guideline or templates using in Jamaica, created by the LICJ. And we also see this template. How does it work? How look like its structure? What are the mandatory and maybe optional items you have to use, and you can use as a metadata, as a description of your data sets. After the break, in the second part, we started on the slide. So in the second part, we will see some practical aspects of them. As you already know, Geza mentioned, there will be a practical workshop in Kingston, Jamaica at the end of this month, and there will be used RGS platform. And in this platform, we will see how to deal with the GIS data and how to check the data quality in the geometry and the attributes as well. So here we will talk in theory about the topology. What does it mean? How does it work? What are the topological relationships? How does it manage inside the geodatabase in RGS, of course? What is an invalid geometry? How can we check and repair it? And we will also talk about the invalid spatial references. When a coordinate reference system we talked about yesterday is missing, how can we fix it, for example. And there at the end, we will see through some slides an extension of our GIS, which is the data reviewer extension, which was developed to check the data quality, to search for errors in geometry and attributes as well, and to fix them. So this is the schedule we try to cover today. And yeah, just a note, if you have any questions about the topics, please type your questions in the chat box as well. We will also collect them and answer them after the workshop in text. So feel free to write your questions in the chat box. Okay, let's start with the data quality. First of all, the definition. Of course, everybody knows about something about data quality, but in general, we can say that the data quality is the degree of data excellency that satisfies a given objective. So it is a relative things. It's depend on our goals, or the application we are doing. And concerns about the quality of spatial data have become more prominent in the recent years because different or several reasons. One of them is that the data production in the so-called private sector is increased, which means the standards in data collection or the data formats are not so homogeneous in this case. When you are when the data sets coming from different sources, they are very heterogeneous. Another reason is that the use of GIS as a decision support tool is also more and more important. So the reliability of the role of the GIS is increasing, and also increase the reliance on secondary data sources. So we don't go out to the field, for example, to collect new data sets, but we are using so-called primary data, and we collect, retrieve data from that base, and that's mean we are creating and we are using secondary data sources, data sets. The data quality can be differentiated in space, time, and thematic dimensions. We will see that in the metrics as well. That, for example, the accuracy means have different meaning in the space, time, and accuracy dimension. In general, it can be categorized. So data quality can be categorized into data completeness, data precision, or resolution in this spatial topic, data accuracy, and data consistency. If you want to define them in one short sentence, we can say that the data completeness is the measure of totality of features. We will detail it later, of course. The data precision, or the resolution, is the degree of details that are displayed on the database we are creating. Data accuracy is the discrepancy between the actual values and the coded value. It can be a coordinate, it can be an attribute value, a thematic. Yes, it can be also a time-based property of the data. And the data consistency is the absence of conflicts, any conflicts in a database, and we will see later what kind of conflicts can be appear in a spatial database. Sorry. Let's start with the accuracy, because I think this is a easiest to imagine what is it, how it is working. So we can say that the accuracy describes how close a measurement is to its actual value and is often expressed as a probability. For example, we can say that we are measuring point locations, point coordinates with a simple handheld GPS or with the GPS sensor of our mobile phone. And for example, 90% of the measurements will be in a 5-meter buffer of the actual location, of the real location, real coordinates. The inverse of the accuracy is the error, and we can measure the error. And this error can be measured separately for time, space, and team. It is what I have mentioned before, that the data quality can defined in space, time, and team dimension. And these measurements in space, the accuracy in space, or the spatial accuracy, temporal accuracy, and the thematic accuracy are not necessarily independent. I have a example. Let's describe it for you. Consider a data set dated in 2000, for example, that depicts a 2-lane road. But assume that in the late 1999, so 1 year before, the road was converted into a 4-lane motorway or highway. This is both a thematic error, because there isn't a 2-lane but a 4-lane entities there in the environment, and it is also a temporal error, because the date 2000 or 1999, 2000 is not a true date, because the information we have stored in the database, the 2-line road, it is, we can say, outdated in 2000, but it was true in 1999. Or another example, the soil mapping units, when we want to delineate soil patches in the environment, and as we mislocated this boundary, it is a spatial and a thematic error as well, because a spatial error because the boundary isn't on the right location; it is moved or shifted in every direction. It is also a thematic error because on the position, for example, next to the border or the boundary, there is another soil type in the reality. So this is a short, just a short example to understand that these spatial, time, and team dimension isn't necessarily independent. As we see this definition of the accuracy, it is required that we have to know the truth, but it isn't always exists. For example, you can imagine a shoreline. We cannot say that the shoreline is there or there, because it is a changing phenomenon, of course. And of course, this truth can be observed as well. Think about the historical data. We cannot observe the historical data now in the recent time. So that's the problem of true, and because we can have problems with the measurement of accuracy as well. So the accuracy is a relative measure rather than an absolute one. Since it depends on the intended form and content of the database. We will talk about later. So it is important to see that it is a note. It's a relative measure. Let's see these three different aspects or dimensions of accuracy. The first one, the spatial positional accuracy, which has two components, of course. It has a horizontal and the vertical components as well, and it can be a systematic. I mean, the error, of course, the inverse of the accuracy can be systematic, which is a bias, or it can be random as well. Let's see how to measure spatial accuracy. There are different statistics we can use to measure. For example, we have several measurements, and we compare the measured and the actual values, measured and actual coordinates, and the differences, which is an Euclidean distance in case of a point geometry, can be used to calculate the mean error or root mean square error. These are quite simple metrics which can be calculated and these are quantitative units, of course. Okay, it's a bit more complex, the spatial accuracy in case of a line segment, for example, a line object. It is more or less a buffer around the real position of the line. Okay, let's see the temporal accuracy. You can say that the temporal accuracy often equated with the currentness, but they aren't necessarily the same in every cases. You can say that the temporal accuracy refers to the arrangement between the encoded and the actual temporal, we can say, coordinates. But the currentness is an application-specific measure of the temporal accuracy. The currentness refers to the degree to which the database is up to date. Okay, we can say it is the measure of the the degree of which the database is up to date. And in this case, the database can achieve a high level of temporal accuracy without being current, and we can think about again the historical data sets, for example. They store historical data. They aren't current, of course, but they can be accurate in the temporal dimension. Okay. And the third aspect or dimension of the accuracy is the thematic or attribute accuracy, which can be measured different ways. These metrics are different for the quantitative and the qualitative or categorized data or data sets. For a quantitative data, can measure similar to the spatial accuracy, calculate distances and calculate root mean square errors and so on, or calculate differences and root mean square error from the differences. And for the qualitative or categorical attributes, the classification accuracy assessment is a commonly used method. When we have satellite imagery, for example, and we have done a classification on using that data. We have different classes, of course, and we can compare the classified and the true value of, for example, of the land cover on a pixel in a raster data set, and different metrics like the overall accuracy or the producers or users accuracy or the kappa value can be used to measure this type of errors or the accuracy, this thematic accuracy. Okay, and yes, in case of qualitative attributes, we can create this error matrix, and as I mentioned, we can calculate producer user accuracy or the error of omission and the error of commission as well. They are the same, but the inverse of the users and producers accuracy. Okay. Let's see the precision of or resolution in the spatial, in case of the spatial data. The resolution is the amount of details we can that can be discerned in a data set. It is clear that the data are of limited, let's see, precision. All data are of limited precision because there isn't any measurement techniques which is infinitely precise. And of course, the geospatial databases are intentionally generalized. So the generalization is a very important part of the geographical modeling of the environment, you can say. This generalization includes elimination and merging of entities or features, the reduction in details, smoothing, thinning, and aggregation of classes. So we can generalize the spatial component of the entities, the attributes, the thematics as well. The resolution of the database must match the level of detail required in the application. So it's very important, as I mentioned before as well, that this matrix is also a relative metric. It is based on the application. So if we need for a small scale analysis, it's satellite imagery with 500 meter resolution is enough. In that case, it can be a precise data set. But in a local analysis with the large scale, we need a much better resolution. Aerial photographs, for example, in some centimeter pixel size and so on. Okay, the precision has also the spatial, temporal, and thematic aspects or dimension. The spatial resolution is the minimum size of objects on the ground that can be concerned. In a raster data model, it is the size of a pixel because the pixel is the basic element in the model. But in a vector data model, when we are working with vector data, the resolution is the minimum so-called mapping unit size. So we can say that we map only the patches, I don't know, for example, water inundations on the ground, which are greater than, I don't know, 1 hectare, or just say a number. Okay, so there's a distinction between the raster and the vector model, and the meaning of the resolution in the raster and the vector model. Normally, we can say that the resolution, the so-called sampling rate, are equal, or more or less equal. So the resolution is the pixel size of the minimum mapping unit, and the sampling rate is the distance between the locations where we can measure or we can collect the data. Let's see the temporal dimensional aspect, the temporal resolution. The temporal resolution is the minimum duration of an event that is discernible. It is very important that it is affected by the interaction between the duration of the recording interval. This is the measuring method, it's based on the measuring method, and the rate of change in the event. Okay, so if the event with a lifetime less than the sampling interval are generally not resolvable. So we cannot measure events which change faster than the temporal resolution of the measurement method. Okay. So there is a clear distinction in this case between the resolution, the temporal resolution, and the temporal sampling rate. You can think about, again, the remote sensing data, satellite imageries, for example, or sensors or satellite sensors have a so-called revisiting time, which is the sampling rate, which is the time period in which we can repeat the measurement. But the temporal resolution is the duration of the measurement with one measurement. Okay, and the third one is the thematic resolution. The meaning of this thematic resolution depends on the measurement scale, similar to the previous slide we talked about. It is different. It is different in quantitative data. It is determined by the precision of the measurement device. So we can measure, for example, temperatures in 1 Celsius for precision, for example. I know it can measure it more precise as well. But in case of the qualitative, the categorical data, this thematic resolution is the fineness of the it depends on the fineness of the category definition. So if we define, for example, 1,000 different land cover categories or land use categories, or we can just define 5 different categories. Okay. Let's jump to the next metric. We talked about the accuracy and the precision or resolution. And now let's see the consistency. Consistency refers to the absence of apparent contradictions in the database. And as I can see, the conformance with certain topological rules we'll talk about later more detailed. For example, only in a location, only one point can exist in the database for some reason, or the lines must intersect at nodes, intersect and cut them at nodes, or the polygons are bounded by lines. There are different topological rules. All of them are in the topic of the topological consistency. So the topological consistency means that there isn't any topological errors or errors in the data set. Or inconsistencies. The spatial topological consistencies can also be identified through the redundancies in the spatial attributes. For example, we have duplicated the vertices along a line, or we have duplicated features, whole features, for example, and so on. The temporal topology, again, another aspect or other dimension of the metric, is the inconsistency exists if a different entity appears at the same location of the same date or same, we can say, time or if an events have temporal overlaps, for example. And we can define the consistency in the thematic from thematic aspects as well. Redundancies in thematic attributes. For example, you have a database about the counties in the country, and you have a population attribute, total population. You have a mean household size attribute, and you have a total number of households attribute. Of course, there is a redundancy because you can calculate the mean household size from the population and the total number of households. Okay. The absence of an inconsistency, it can be spatial, temporal, or thematic, does not imply that the data are accurate. Okay, because there are other aspects as well. Inconsistency is appropriately viewed as a measure of internal validity. So the validity of the data, validity against different rules, predefined rules, have to be checked to measure the consistency of the data. Okay, let's see the completeness. The completeness refers to the relationship between the object in the database we have stored in the database and the so-called abstract universe of all such objects. This abstract universe can be defined in terms of a desired degree of abstraction or generalization. So as we model the system, the environment around us, we have to define different selection criteria or definitions and other mapping rules to create the database, because we are only interested in for example, the trees in the city. It doesn't matter the street or the road network. That means there isn't any error of the completeness that we don't have streets in the database, because we didn't interested in the roads in the roads in this abstract universe, which is the results of selections and definitions and so on. We only have the trees, for example. There are two different types of completeness. There is so-called data completeness and the model completeness. The sorry, the model. So the data completeness is a measurable error of omission observed between the database and the specification. So we have all trees in the city in the specification, database specification. We want to have all trees in the city, but actually in the database we only have, I don't know, 90% of the trees. So this data completeness is used to assess the data quality. For example, in the metadata, in the data quality parts of the metadata, we can store this information and share this information with the users who will use our data set.
Excuse me, Zalan.
So in a highly generalized database can be complete.
Zalan?
If they contain all the object desired in the specification. So that's the point, that we have to have all the data that we have specified in the beginning, as we have started to build up a database. Okay, the model completeness is another type of completeness, another aspects. Refers to the arrangement between the database specification and the abstract universe that is required for a particular database application. Yeah, it is another level completeness, this modular completeness. And we can also talk about feature, attribute, and value completeness. So we can assess the feature completeness, the attribute completeness, and the value completeness. The incompleteness of the features can be in the spatial, or in space, time, and theme as well. And the attribute completeness is the degree to which all relevant features, all relevant attributes of a features have been encoded. For example, we have a attribute table with a lot of fields, attributes, but we have a lot of no data fields inside because we didn't fill or didn't collect these attributes. Yes, and the value completeness refers to the degree of which values are present for all attributes. Okay, the completeness is typically defined in terms of the omission, error of omission, but it can be also include the so-called error of commission. For example, we want to collect the trees, the database, but accidentally we also collected some buildings, for example, into the database. It is a commission, of course. Okay, let's see some examples of from with spatial data. They are from the ES3 online hub. An example of the completeness. It is as you can see, that the presence or absence of a feature, their attributes and relations in a data model. This is the completeness, in other words. And in this example, you can see that there is some missing building footprints in this database compared to the base map or area photographs. We only have 2 features, and we have I don't know, 6 missing footprints in this database. The logical consistency is you can also read that the degree of the adherence to predefined rules. So we have predefined rules, and the data set has to fulfill all these requirements. And for example, 2-lane roads, a motorway, for example, don't have gravel type surface, for example. But in this data set, we have this gravel attribute as a road surface type, which is inconsistency, a logical inconsistency, because based on the standards or predefined rules, a motorway or a highway has to be a concrete, for example, concrete or asphalt surface. Okay. Spatial accuracy, maybe it is easier to realize and to imagine how it is works. So we have a feature, a geometry, but it is shifted from the real position, which is represented by an aerial photograph, the base map. The next example, it's a thematic error. We have a pool, water pool on the base map, but it was digitized. Okay, it's corrected. The geometry is fine, it's correct, but the thematic, the attribution is wrong because it is captured as a wetland, for example. Temporal quality or temporal accuracy in this case, in this example, that we have runways in an airport, but some of them is also out of work, so it is already closed. But in the database, it is still signed as a as a working runway, for example. And the data usability will show us that the data set fulfill the requirements to a predefined goal. For example, this map, which can be seen here on the figure, it is used to
Sorry, Nalan. Can you stop shortly because
visualize, for
sorry.
example, national parks because of the scale, but it isn't useful to map, for example, a city scale phenomenon like the road network in a city. Okay. Let's see some. Sorry.
Igazán csak annyi, hogy szeretnének kérdést föltenni, állítólag a chatbe is írtak, bár én se látom, az Alicia szeretne kérdést föltenni.
Sorry, my colleagues warned me that you have questions in the chat box. Sorry, but I cannot see it. I see my on my screen the presentation. First precision slide. I tried to go there. It was it. And who was it? It was Teresa. Sorry, Terra.
Yes, thank you very much. That's the slide I just wanted to have a quick look back at. Thank you.
Yes. Terra, you can also type your questions in the chat, and if maybe you already typed it now. Okay, I will continue.
Yes, please, thank you.
Do you hear me?
I got to see what I needed to see. You can continue. It's appreciated.
I think you can continue, Zana. Yes.
Do you hear me, Geza?
Yes. Yes, I hear you.
Yes, continue. Please go ahead.
Go ahead.
Hello,
you
hello,
can
hello. Hello, hello,
you
hello.
Can continue. Everything is okay. You can continue.
Hello, hello, hello.
Please go ahead. Please, please.
Okay, thank you. So you can hear me. I can continue. Okay. I had an alert that I have some problem with my voice. I don't know.
Yes, you can go ahead. Yes, I had said that.
Okay. Let's see some sources of the discrepancy in spatial data. Why we have errors? Precision, for example, on the consistency and so on, or the completeness. One of the source of the root of these errors it's come from the data information exchange, which is basically the information about the data provided by a client or organization who were created this data set. It is important the degree of information, we can say it's a metadata, which was provided by the client, defines the accuracy and the completeness of data. So that's because it's very important to manage your metadata always up to date and share your metadata with your data sets. The second one is the type, the data type and the data source, because as you know, there are different file formats which can be used to store spatial data. And as I also mentioned that a lot of data producers are working and creating spatial data. So, and these data formats have some limitations. For example, the S3 shapefile format cannot manage the topology, for example. So if you want to have this kind of accuracy or consistency in your data, then you have to use a data format like geodatabase, which can manage the topology. Okay. So it's important to identify and evaluate the data type and the data source before doing any processing on your data. It's also important to see the data capture, the method of the data capture, because you can use several GIS platforms, and there are different tools to collect data, for example, digitizing maps. But the user who do this process, this digitizing process, this data collection, can misinterpret, for example, the base maps, and and digitizing, for example, 2 buildings instead of 1. Of course, there are tools which can be used to check and fix these type of errors. We will see them in the second part of this workshop. But it is very important in general that this data capture workflow or processes will be performed on the perfect scale, where the user or the user can view the features instinctively. So so this is a source of discrepancy as well. Then the cartographic effects, like the symbology, the colors, the size of the symbols, also must be assigned according to the domain of the feature. For example, if you are working in the domain of forestry, we are working with parcels and trees and different roads. Then we have to use the corresponding symbols for the visualization. The data transfer can be also a source of error. It is connected to the data file formats, and the metadata. I mentioned the first point as well, and we will talk about in the second part more detailed. It is very important, first of all, to have the metadata and to update them regularly and share with the data set itself. There are different techniques to improve the data quality, of course. For example, you have to choose relevant data from the relevant source. You have to derive the precision from the origin itself. The data quality has to be tested in each phase of the data capture, so many times if it is needed. There are different tools in GIS platforms which can be used to automatic evaluate different errors and to evaluate and assess the data quality and spatial and non-spatial data as well. And of course, you can assess the mode of the data are used and the users itself, and determine the map elements, scale, visualization, feature orientation in the right way. Okay. The following figures also is coming from S3, and it's about how to define the data quality requirements. As you can see, there are variety sources for the quality requirements that can be applicable to identify the data quality requirements. And the implementation of the quality control processes. So there are requirements from the industry of GIS parts. There are requirements from the clients. There are regulations of your organizations, for example. They all define the final data quality requirements. Okay. Let's jump to the metadata, which is a very important topic in the frame of this project as well, because it it's not enough to have the data, the spatial data itself. You won't use it and effectively unless you have a good metadata next to them. So let's see the definition and the importance of metadata first. In general, we can say that metadata is the data about the data or the instruction manual for data. So it describes the who, what, when, where, why, and how of data. This is from your metadata handbook. So what geographic data set we have, what is the title, what is the description, short abstract of your data, of the content of your data set, who is collected it, who was the originator or the creator of the data, the supplier of the data, how was it collected, what was the method or the methodology used, how can we obtain the data set download from website, for example, or how can we obtain more information about the data set, who are the responsible party or the contact persons can ask for about the data, how can we order the data, what kind of formats, in what kind of formats available the data, what are the constraints, the access and the use constraints. When was it created? It is the temporal aspects of the metadata. What is the date of the creation? What is the is there, if it is an update cycle of the data set or not? Where does the data reside? So what is the geographical extent? What are the bounding coordinates of the data set? What is the spatial reference, the coordinate reference system which is used, and so on. So metadata has to be detailed, dependable, and well documented. So it's very important not to have a metadata with some items, but it has to be as detailed as possible. Geospatial metadata describe, of course, spatial data or spatial resources. We can say it can be maps, spatial data sets, or services as well. Metadata is very important, makes the spatial information or data sets more useful for all type of users, of course. And metadata not only helps to find the data, but if it's already found, it also tells us how to interpret, how to use effectively the data set. Okay, can be the benefits of the metadata in an organization. For example, it provides an inventory of the data assets you have. It can help to determine and maintain the value of the data. It can determine the reliability and the currency of data. It can support the decision makers and the decision-making process. It can be a document of different legal issues. and it helps have to keep the data accurate and have to verify the accuracy, of course. And the goal is to have good decisions and, of course, saving the cost. And it also helps determine the budget because it provides a clear understanding of when and if data needs to be updated or be purchased, so on. Okay, some characteristics that define the role of the metadata in your, we can say, spatial data infrastructure, a term from yesterday. We can talk about the availability, which means that the metadata will shows us and determine the sets of data that exists of a given geographical location. Where do you find look for data sets? It is used to define the fitness for a given use of the data set. So it determines if a set of data set meets specific needs or not. It is useful for your application or not. It can define the access. It is available for you or not. And it can also define processes and where through you can use your data, and how can you acquire the data set. Sorry. Let's see some metadata standards. I listed here 3 different standards: the FGDC CSDGM. This is the standards of the Federal Geographic Data Committee from the United States. This is the one of the first metadata standards from the middle of the 90s. The ISO standard, the Jamaican metadata template or standard is based on these ISO standards. And in Europe, there is a metadata regulation connected to this INSPIRE, this big spatial data infrastructure idea. And you can see these on this slide. So the metadata standards they provide or define a framework, a common framework from describing, managing, and sharing information about our spatial data sets in a consistent and interoperable manner. So the interoperability is an important word here, that you can use it independently from your GIS environment. In an RGS platform, on an open source platform, you can use the same way these descriptions, these metadata. Several committees, like I mentioned, the ISO, the Federal Geographical Data Committee, or the European Union have developed their own guidelines for metadata to best suit their particular requirements and needs, of course. And you also have your own standards. Okay. The next slide will show you a general structure of an overview and the comparison of the 2 standards, the ISO and the CSDGM standards. They have more or less the same categories, because the items, the descriptive items, are categorized in groups like the identification information, data quality information, spatial data organization information, spatial reference information, entity and attribute information, distribution, and the metadata reference, so information about the metadata of metadata. And the ISO is the same, but the structure is a bit it's visualized different way. But the point is the same, I think. Okay, let's see a bit more detail these categories and the most important items inside these categories. So in general, metadata gives the following information: the title of your data set, a description of your data set, information about the data source, the creator or originator of the data, or the owner of or the supplier of the data set. Then it will provide information about the how, the methodology, how the data was obtained, how can you order the data, what kind of formats are available, what are the constraints, as I mentioned in other slides already. There are temporal informations as well, the date of creation, the update cycle, if it is any, and information about the spatial extent of the data set and the spatial reference system, which is used to define the coordinates, of course, in the data set. So the main groups of these metadata items are the identification, general informations, the contact items, responsible persons, email, phone, and so on, addresses, and so on. The quality, about the quality of the data. This is the data quality assessment, we can say. Information about the spatial reference, mainly the coordinate reference system. Information about the entity, what kind of data model were used, vector or raster data. If it is a vector data, they are representing the entities with points, line, or polygons, and so on. A detailed description of the attributes, because, for example, in case of the shapefile formats, you know that in the attribute table, you can use only field names with maximum 10 characters, as I remember correctly. So you have to have a more detailed explanation of the attributes, because this abbreviation in the header is maybe not clear. Or the domains, which is the corresponding domains to the attributes. For example, for row types, we can use 4 different values only. It can be defined as a domain previously. The lineage group and the items in the lineage category will describe the history of your data, what kind of processes were performed on this data set. For example, the ArcGIS will log all these information automatically into the metadata of your data set, and you can scroll back in time in this history and check the steps, the different processing steps, and the parameters of the processings as well. There are legal information, for example, constraints of the data access or the usage of the data. Temporal information, I mentioned before, the creation of the data, time resolution, the update cycle, and the reference, metadata reference, who is responsible to update the metadata, for example, when was it last time updated, and so on. Some more details about these items. In the identification group or category, you can find a brief description of summary of your data, the title of the data set, the description or keywords, which are very important in the search processing. If you want to find some data set in a data repository, for example, in the first step, you will type some keywords in a search field or panel on your GeoPortal, you can say. In the contact information, you can have the originator who developed the data set, or the publisher who assist the producing, editing, and the finalizing of the end product, or the distributor, who focus on making the data available, and so on. So different contacts, okay, name of the person, of course, and phone numbers and email addresses, organization, and so on. The quality will explain the accuracy and the standards that was used to create the data set, because the data quality is, as I mentioned, it's a relative measurement. Is always based on the standards which were used to collect and create the data set. Okay, here I already listed the horizontal and vertical accuracy by other data quality assessments can be stored in this section of the metadata. A spatial reference type will show you the applied geographic or projected coordinate reference system, the geographic extent, bounding boxes, or you can also use so-called geographic keywords describing the location of the area of the data set, or you can also create thumbnails from your data. The entity and attribute group will describe how to represent the spatial information in the data set. It is a point, line, or polygon geometry, or a raster data set. And if it has attributes, what is the meaning of the attributes in the attribute table? What are the valid values? Is there any predefined domains, for example? What are the predefined unique values for attributes, and so on. Yes, I also talked about the lineage. It describes the sequence of operations, processes that has been applied to the data set, and it also described who and when was processed the data. So you can contact them and ask them why and how to process the data set previously. Okay, the legal parts will outline the constraints for accessing and distributing the data. Can you share your data, the data set to others, or you can only use it if you pay for it, for example? And describes the liability also to ensure the protection of privacy and intellectual property, and includes so-called security classification. For example, a data set can be confidential or restricted use or sensitive from some reason, or are restricted or maybe unclassified if there isn't any information about the security aspects of the data. The temporal parts describes all these time-related properties of the data, like collection of the time of collection, the time range which was covered by the data set, the time of validity when it was validated, the update frequency, and so on. Okay. Metadata reference. This is the last part of each metadata standards. It will describe and provide information about the responsibility regarding to the metadata itself, contact information, who has created the metadata, when was it created, when was it updated, and so on. Okay, these groups and items are general items. We can say in most metadata data standards you can meet with these type of informations, metadata. Now let's see some errors, or you can see here it's most common errors. It is also from your metadata guidelines. Is 10 points. There are some interesting hints or tips to about the metadata creation process. For example, it can be a source of error that you want to define your metadata too finely or too broadly, or if you misunderstand the meaning of resolution, for example, or you put too much faith in metadata editors or metadata tools. There are different tools, software tools to create metadata, to validate your metadata. In the ArcGIS platform, this is a built-in capability, so you can manage your metadata in ArcGIS. And we will see that in the practical workshop in the end of February as well. Or yes, or you think of metadata as something you have to do at the end of your data creation process, but it has to be created and updated continuously. And the worst case is that you do nothing, you don't care about the metadata, because the users won't understand your data set, won't use the right way your data set if you don't share the metadata as well. Okay, and let's see your metadata guidelines. It has selected elements from the ISO standard, as I mentioned, that were considered applicable to the Jamaican environment. It has these categories of the elements, like the identification, data quality, spatial data organization, spatial reference, entity and attribute, distribution, metadata reference, and we will run through some tables, and you will see that there are mandatory and optional items or elements. Of course, the mandatory items has to be filled when you create your metadata, and the optional one are optional. If you have information about them, you can define them, of course. The table is maybe it's familiar if you know these guidelines. For example, in the identification category, you have to define the originator of your data, the publication date of your data. You have to add a title of your data. You have to define the representation form of your data. Information about the publication. So how can you publish this data set? You have to add a bit longer description, an abstract of your data. Then you have to define the time period of your data, which is covered by the data set. The status, it is the finalized data set, or it is we can say under construction. The spatial domain, the area which is covered by the data set, or access and use constraints, of course, credits. So you have to recognize of who contributed the data set. Security information, I mentioned it is I don't know, is it private data or other concerns, which was the native environment where the data set was created. For example, what kind of file format, which software environment, and so on. In the data quality section or group, you have to define the accuracy of your data. Don't forget that the accuracy has spatial, temporal, and thematic aspects. You have to define and add a so-called completeness report, which will describe that you have, I don't know, stored 90% of the real entities which were defined in the database specification, and the lineage, that kind of processing was performed previously on that data set. Yes, you have to define the horizontal and the vertical coordinate reference system which is used by the data. You have to add detailed description to the entities, especially to the attributes, to explain the meaning of each field, each attributes on the attribute table of a feature class. You have to say and store the information about the distributor, contact informations, addresses, phone numbers, emails, and so on. How can you order the data set? It is a free data or you have to pay for it. And as a metadata reference, so information about the metadata, you have to store the date of the creation of the metadata, or the review or update of the metadata, and contact information as well. Yes. Okay. I think we can finish the first part, and we can have a short break, 15 minutes, which means we can continue at 40. It's good for you. It's a bit more than 15 minutes, maybe 17. Okay. Thank you. Okay. We can continue. Do you hear me?
Yes, we hear you.
I cannot hear you, Geza, but I think you can hear me.
I hear you.
Okay, thank you. That's fine. Now I hear you. Okay, before we continue with the data quality checks and different methods to find these errors, I want to show you an example of a metadata file, which is an XML in XML file format, and I have to change my screen sharing. A moment. Okay, now you can see my screen. I hope maybe it's too small. So this is a metadata of the admin zones of NSW and MA, I don't know, some type of boundaries in Jamaica. And inside the metadata, you can see these groups of items or categories, like the identification info, the data quality section, the spatial data organization, the entity and attribute info, the distribution informations, and the metadata reference part. And if we open these sections, you can see the details. Some of the items are empty, as you can see. For example, there isn't any citation or description or time period defined, and so on. But there is an access constraint, for example, defined here, or a use constraint as well. There are information about the creator of the data, the organization who has created this data set, and versioning of the software and the data set itself, which were used. There isn't any identification information in this sample file, but we have some data quality and lineage information. I hope there is. Not so much. We can say that it is nothing. Let's scroll down And for example, here in the spatial data organization, we can see that it is a vector data set. And we have another much more detail that they are polygons, geometries. I don't know what does this count mean. Maybe it's not so important. Then we can see the entity and the attribute informations. Here in the entity type, you can see the name of the feature class, we can say. And then we have several attributes. And inside these attribute items, you can see, okay, the first one is a default built-in ID, an object ID. I try to find some, this is the shape field, storing the geometry, of course. This NSW zone, this is the name of the attribute. You can see that in the header of the attribute table. And there is you can say, more detailed information about this attribute, some kind of zones. Comments. Okay. Now, for example, here the shape length field. This is the name of the field. There is a longer explanation. This is it is stored the length of the features in internal units, which means the unit of the spatial reference system. We have the same with the shape area field, of course. Okay, we don't have too much information inside this metadata file, but you can see the structure, that it is a XML file. You can edit in a text editor, of course, or you can edit and update inside ArcGIS or inside any GIS platform. And I try to show you the same metadata in QGIS. Just a moment. This is, I hope to find, try to find the same data set everywhere. These are okay, this is it. Okay, I changed my screen sharing. Just a moment. Jumping to QGIS. I add to the map this land use Jamaica data set. And if I check its property, the layer properties, there is a metadata tab where you can find more or less the same categories. And the information from the XML files are loaded here into these fields and yes, into this dialog. You can edit here, of course. There are the constraints or the extent. It is calculated automatically from the spatial parts, from the geometry of the layer. Here you can see the coordinate reference system information as well. Some contact information is also stored in the metadata, and you can of course add additional contacts if you want. There isn't any history, lineage in this case. And this is a validation, which means the software try to find the mandatory fields or items of the metadata where there isn't any defined content. For example, here is listed a contact and the license item of the metadata, which are now empty. So to validate based on a standard, of course, a specification, you have to fill and add values to these items, metadata items. Okay, it was just a short example of metadata. We will work in GIS with metadata at the end of February in Kingston. Okay, now let's go back to the slides and continue with sorry, it isn't it. And continue with the GIS data quality check, or methods or methods to check the data quality, spatial and in attributes as well. First of all, we will talk about the topology. What is a topology? Topology expresses the spatial relationships between connected or adjacent vector features, like points, lines, or polygons, of course, in a GIS. So it's about spatial relationships. It's very shortly we can say that. It is useful to detect and correct spatial or geometric errors coming from the digitizing process, for example. And it is also necessary to carry out some type of spatial analysis, like network analysis. You want to find the best route, the shortest route between 2 points along a street network, for example, and so on. Features can share their geometries in several ways. There are 3 categories of these relationships. The adjacency means that the features share a common boundary. For example, you have 2 polygons, for example, 2 parcels, 2 neighboring parcels. They will share the boundary. So you won't store the boundary edge twice in the database. You will store it only one time. We will show that in the following slides, because they share this geometry. The 2 polygons share this geometry. The features can, this relationship can be a connectivity when features are connected via a path that connects them. For example, you have 2 nodes or 2 point features which are connected with a line segment or a line, for example, a road. 2 intersection in a road network, street network are connected, are in these relationship, these connectivity relationships via a path, via a road or a street. And the features can contain each other as well. A feature is contained by another or within another feature if it is completely inside the other feature. Okay, these are the most important categories, and through the topology we can check these relationships and we can fix them if there is any issue in the geometry. Yesterday I already showed you or your colleagues these slides, because in the GIS, the topology is implemented at the data structure level. So we have to store the geometry of the features to do later all kind of topology processes. In this slide, you can see 2 different examples. The upper one is a polyline feature class. We have streets. Sorry for the street names; they are Hungarians. But let's focus on the geometry. So you can, and you have to store of course, the lines with all their vertices, with the nodes, the start and the end nodes as well. But it is enough, because you have to also store the nodes in a distinct table with their IDs, of course, and coordinates. And you have to store the connection the relations between the nodes and the edges. So from which node or how to connect the edges in a given nodes. Let's jump to the following slides, and here you can see these tables. So you will have a table, a so-called node table, with the node IDs and the coordinates of these nodes. We have a line table with the line ID and the start and the end node for each line. And if a line has internal vertices, then we have also stored the vertices, the coordinates of the vertices, but we don't have to store here again the end and the start node coordinates. And we have a third table where which will define the connection between the nodes and the lines by adding for each node the connected line IDs here. I jump back for a minute. The other figure in the bottom is a polygon geometry. We have parcels or doesn't matter, we have polygons, and it isn't enough to store the polygons and the boundary of the polygons and the vertices of along the boundaries, but we have to store again the nodes which are signed with the numbers here and the red dots. We have to store the edges as well. These are the letters, small letters, and we have to store and describe the polygons with the Roman numbers as well. So we will have 5 different tables, one for the nodes with the node IDs and the coordinates, one for the lines with the line IDs, the start and end node IDs, and the internal vertices if it is along the line. We have a polygon table with the polygon IDs and the boundary edges or lines defining, we can say, the polygon. And of course, we can add attributes to the polygons because the feature is we want to describe is the polygon, of course. Then we have a table describing the connection or the relationship between the IDs and the lines here in the lower right corner with the node ID and the connected line IDs. And we have a fifth table which will define the connection between the lines on the edges and the polygons. So each line has a left and the right neighboring polygon. So it means also that all lines has a direction, and the direction of the line will be defined by the order of the nodes, the start and the end nodes. For example, the line A is running from, sorry, I have to go back, running from node 1 to node 2. So this is the direction from up to down. And in this sense, the left neighbor is the polygon 3, the third polygon, and the right one is the polygon 1. You can see that here in this table. Okay, this is the data structure behind, which has to be defined and stored in this way to use the different topological functionality in a GIS. Okay, let's see these topological relationships. So the topology is an arrangement of how point, line, and polygon vector features share their geometry. A topology can constrain how features share geometry. I mentioned it previously, so they can be neighboring polygons, they can be inside each other, or they can be connected. So these constraints, based on these constraints, and adjacent parcels have shared their edges, of course, the common edges, the common line of the boundary. The topology can also define and enforce data integrity rules. For example, we can define a rule that the polygon of the parcels inside the settlement cannot overlap each other, or it isn't allowed to have a gap between the polygons. Of course, they have to share their boundary. So it means a topology can define and enforce data integrity. Topology support different topological relationship queries. For example, you can look for adjacent features, and it also supports different editing tools that enforce the topological constraints. So you can edit a common boundary of the adjacent parcels or vertices or a vertex on that edge, and both polygon, the geometry of both polygon, will be updated after this editing step. And the topology can construct features from unstructured geometry. You can see unstructured geometry. For example, we have lines. We have a line feature class, and of course, this line represents the boundaries of parcels. For example, it is coming from a CAD file, and you can convert them. You can build up the polygons from these lines. So we can say that the topology is a collection of different rules. We will see them later, coupled with a set of editing tools and techniques, and enable the geodatabase to more accurately model the geometric relationships. Okay, so they are rules, and they are editing tools which can ensure to fulfill all these rules, the geometry. In GIS, this topology, so the rules and the feature classes which will be part of the topology. So everything is stored in a geodatabase. So you have to use this data storage format, the geodatabase, and the file geodatabase especially. And it is stored as a description of how the features can spatially related. So the edge sharing, connectivity, containment, and so on. Okay, in this slide you can see a big figure, which it is available online, of course. They are all the available relationships, or so-called topology rules, which can be used in ArcGIS. I try to open it. It will open in a browser. Sorry, maybe I have to go back, and there is a link. No, I have to change my mouse pointer this way, and I will change my screen sharing to this one. Okay, and now we will see the content of this big poster. Okay, from a bit distance, you can see different colors. We have topology rules for polygons, for lines, and for point geometries as well. And so these are the groups. And there is one rule. There is one rule which can be applied for line and polygons as well. And a small extension and representation of the rules of how does it works are also provided here on these small rectangles. For example, we want to see all of them, just some examples. For example, we can say that it is a very common case. We can say that the polygons cannot overlap each other. They must not overlap each other. For example, we have voting districts, as you can see here in the example. Yeah, the polygons of these districts cannot have any overlaps. If there is any here in the red part, you can see the software will find these parts of parts of the polygons, and it will highlight this part, and we can fix them in using some tool, or for example, you can merge them into one of them, or we can delete this part. Maybe in this case, the best choice is to merge this overlapping parts to one of the polygon. Another example, a polygon have to contain points. We have in the parcels, and for all parcels, we have to, inside all parcels, we have to have at least one so-called address point where we can store the I don't know, the address or the house number or different IDs of that location. And if some of the points are, or if there is a polygon which do not contain any points, it will again highlight it. Another example, you can have a rule which will say that polygons on different feature layers, feature classes must have covered by each other. For example, the states in these small maps have to cover the counties. Of course, there isn't any counties. There isn't any county outside of the states. Okay, and again, the county which is outside of any states will be highlighted and marked as an error. This is another case when we have to say that polygons cannot overlap each other, but features on different layers. For example, water surfaces and land polygons cannot overlap each other again. Okay, for example, area boundary must be covered by boundary of it again, two polygon layers. You have two polygon layers, and we have an administration unit, level of administration unit, and we have another one on a larger scale. So we have, I don't know, in Hungary we have the country. Inside the country we have region. Inside the regions we have counties. So the boundary of the region has to be covered by the boundaries of the counties or vice versa. Okay. Okay, this is a point relation. Let's say the polygons a bit more, no gaps. We will see similar examples in the practical workshops. I performed topographic check for the counties, or not the counties, but the communities of Jamaica, and I have found some polygons where overlapped each other and where were gaps between. So this is the case when we have gaps. Of course, we have, if we have a, for example, a soil map, soil polygon, they have to cover the whole area without gaps. So if there is any gap, it is an error. So we have to deal with them. We have to fix them. The boundary must be covered. It is similar to the the other case, but here we have a polygon layer, for example, the blocks inside the city, and on the border of the blocks will run the roads, the streets, of course. This is the case now. Let's see some line rules. Dangles. Dangles are line segments that, or end nodes along the line segments that cannot connect to that don't connect to another line. So, for example, dead-end streets are the examples of that. They aren't an error, of course. But for example, a street network of the highways, for example, it isn't allowed to have dead-end roads like this. And the software can mark these nodes, and then we can fix them in for example, deleting these line segments like this. Okay. For example, we have lines on a feature data feature class. Let's say contour lines. So it's a general rule that the contour lines cannot intersect each other. Okay, so if we have intersecting lines features on this layer, it is an error. So we can find these positions, and we can edit the geometry to fix this issue. Okay, that's also an interesting rule that we have. If we have a line data feature class, again, for example, the network of some linear utility, gas or water or something like this, at the end of the lines, we have I don't know, some transformer or meter or something like this, where you can measure the consumption. So this is a connection. This is a relation between lines and polygon geometries and features. Okay. Pseudonodes. Pseudonodes are nodes where you don't have you only have two connecting lines or edges in the pseudonode, so it can be deleted, and the two line segments will be merged together, and it will be a vertex along the line, but it won't be a node. Okay. Okay, and let's see some point related rules, like a point must be inside the polygons. For example, we have a polygon points of the cities. Of course, each city has to be located inside the country or state or any administrative polygons, or it has to be on the border or the edge on the edge of a polygon. In this case, these utility service points have to be on the edge of the parcel polygons. Okay, so there are lots of topology rules which and they can be checked through different routines in ArcGIS. Let's go back to the slides. Sorry, it is it. Yes. And let's see how does it work in ArcGIS using geodatabase, as I mentioned, five geodatabase primarily. The geodatabase includes the topological data model for simple features. So it contains the feature classes, of course, the topology rules, and topological integrated coordinates among the features with shared geometry. So the coordinates of the features on the feature classes, which are integrated or which are the parts of these topology, are also stored in the database. There is a so-called topology layer in ArcGIS. We will work with them where you can see the different type of errors on points, on lines, and polygons, and after you manage these errors, so you fix them, or you make a so-called exception. They will be highlighted in different colors. In ArcGIS, there are several geoprocessing tools to create the topology, to build up the topology, to query the topology, to edit the topology, so modify, to validate, to find the errors, to fix the errors, analyze, and of course manage, like deleting, renaming, and so on. The whole workflow consists of 4 main steps, and we are working with the topology. In the first step, we have to define the rules, of course. So we have a big set of rules which are available in ArcGIS. We have to select from these menu, we can say. And after we define the rule, we have to validate the features against these rules, of course. And the errors were listed, and we can show them. We have an overview of the errors. We can fix them or marking them as an exception. So we will leave them as they were without changing or manipulating its geometry. Okay, the feature classes. So in ArcGIS, I hope you, as you know, in the data storage in a 5 geodatabase or personal geodatabase as well, but we will work in 5 geodatabase. We have the feature classes, and it's very important that the feature classes participating in a geodatabase topology must have the same coordinate system and spatial reference. We'll see later what does the spatial reference really mean. Now we say just the resolution, the tolerance. So it has to be the same. They have to be the same coordinate system and resolution and tolerance. So, and to ensure this, we have to store the feature classes participating in the topology in one feature data set, because the feature data set is defined by coordinate system and the spatial reference, like resolution and tolerance. So it's very important. After that, so after we manage our feature classes in one feature data set, we have an option to define so-called ranking, XY ranks, which means it's about the X and Y coordinates, the horizontal position of the vertices or nodes. This rank in this ranking, a high rank will indicate that the position of the feature in the feature class are known more accurately, or we don't want them to move relatively to feature classes of lower rank during an editing operation. So the features with higher ranks will encode on its original location, we can say, and the other features and the geometry of the other features will modified or changed during this this editing process. For example, as I fixing the errors. The topology rules, as we saw in the previous big picture, are based on the knowledge of the relationships between and among the features that will be taking part in the topology. So the relationships can be defined inside a feature class and between the features on different feature classes. Of course, all of them are participating in the topology. Here are some links to the GIS online help, which will show you and list you the different rules for point, polyline, and polygon features. They are the same as the big picture or big poster we saw. But is maybe we see the first one for points, because here you can also see the default error managing solution, we can say. Just a moment, I change my sharing. So so it was we saw this this type of rule when the points have to be on the edge or the boundary of other polygons or polygons. So this is the initial case. We have points, and some points are or aren't on the edge on the boundary of the polygons. They are marked as error, of course. And we have so the so-called predefined fixes, which is provided by the software by default. Okay, in this case, in this error, there isn't any predefined fix, but you can manually modify the features, start an editing session, and move the feature using, of course, some snap options, moving the features on the edge. Okay, but for example, in this case, when all points have to be inside the polygon, the errors, so the points outside of any polygons, by default will be deleted. So this is the solution for the fix for this error. Okay, and I want to show you the just a moment the polygon rules as well, because yes, you can see that now. We talked about the overlap. For example, this is must not overlap it, so polygons must not overlap each other. We have overlapping polygons. This is the problem, of course. The software will highlight the overlapping parts of areas, and there are two predefined fixes. One of them is the removing of the overlap. In this case, we will have gaps here. Maybe it's not the best solution, but you can also say that you merge the overlapping part to one of them polygon. You can say that you merge to the bigger polygon, or you can select manually the polygon to which you will or you want to merge this overlapping part. Okay, let's go back. You can see these GIS Online help pages later at home if you want. Okay, some examples from the softwares, but only with screenshots. So we have we have different administration units, polygons, except a line of the coastline. So we have to store all of them in a feature data set. It's very important to ensure the same coordinate reference system and the same so-called spatial reference, the resolution and tolerance. So we organized our data inside the feature data set. And then in the next step, we have to create a new topology, and we have to select the feature classes from the feature data set, which will be part of the topology. And it's not enough to select them, but we so it's not mandatory, but optionally we can also assign a rank to each layers. For example, I set it now the coastline for the most precise data. I don't know, maybe it is, maybe not. So it won't be changed. And the other rank, the next level of rank will be the coastline polygon, and then the different type of boundaries will be on the same level in this ranking. So we have a topology with the feature class, with the ranked feature class, and then we have to define different rules. In this example, I defined only only three rules. One of them is it will check the communities layer or feature class, the features on the communities feature class, and we'll look for overlaps between the polygons. And the other one will look for gaps between the community polygons. And the third one will ensure that the coastline polyline, the line of the shoreline, and the coastline polygon are on the same location. So the coastline must to be covered by the boundary of the coastline polygon. I will show you the result of these checking. Here, this is so we define the rules, and we run a validation, and the results of the validation is a list of errors, which can be seen in a table. This is the so-called error inspector table. And I don't know, I had a lot of errors. The errors can filtered by rules, so you can display only the overlap issues, then the gap errors, and then these overlaps between the coastline polyline and the coastline polygon. And here on this slide, you can see that there are several overlaps between the community polygons. It is highlighted on the map as well. Maybe you can see these brighter red parts are the overlapping the section of the boundaries. Yes, the overlap. There are the overlaps. If we zoom in better, we should see the overlaps. For example, if we set transparency for the fill color, that would be visible. So, and as we select one of the error, so it is the selected and highlighted error, we can say that we want to fix them, and there are predefined fixes, as we saw in the documentation. For example, we can remove the overlap. So we will have a gap on that area, on the overlapping area. We can merge the features, merge the overlapped area, the small parts, to one of them neighboring polygons. In this case, I selected this merge option, and here you can see that I can select one of the two polygons, and it is also mentioned which one is larger in area. Or there is a third option to create a new feature, which means we will have a new feature from the overlapping parts, and I think at the end we also have to delete that feature. But in this case, the best solution, the best option is to merge this overlapping area to the largest polygon. Okay, another example is the must be covered by boundary rule. Here you can see there were, I think, two errors, two islands was there. So the polyline, the coastline polyline feature and the coastline polygon feature do not overlap each other. So the polyline has to be on the boundary of the polygon. Yes, but in this case, there isn't any predefined fix. We have to edit the vertices one by one, for example, to use the snap option and snap to the boundary or to the vertices of the polygon boundary. Or maybe it's better to create a new feature, for example, by converting the polygon of this small island into a polyline, and it will ensure that it is covered by the polygon boundary. Okay. In the practical workshop, in the second practical workshop, we will see several examples like this. We will try different rules as well using your data set. Okay, if we are talking about the topology, we also have to talk about the topology editing, which will ensure you to maintain the topological relationships. So the relationships won't change after the editing. For example, if we have neighboring polygons in a topology, like this community polygons, we can edit the vertices along the border or the boundary by editing the edge. So we do not edit the polygon itself. We edit the edge, which is a shared geometry between two polygons. And I try to display somehow that I move these vertices from another position, and as you can see, all the connected lines or edges will move with the node. It is a node. Yes. Okay. In ArcGIS, there are several tools for this type of editing, for this topology editing. I listed here them. I don't want to talk about more detail. We will try them in practice. Maybe it's better. There are the align, age, the edit vertices. I presented it in the previous slide, or the move the vertices, or the for feature, the reshape the feature, or generalize the features. So the point is that the topology editing enable you to maintain the topological relationship when you make edits on your data. Sorry. Okay, after the topology, we also have to talk about the invalid geometry and the invalid spatial reference, because it is also a source of data quality issues. In a GIS, if you perform a geo algorithm, use a geoprocessing tools, it assumes that the spatial reference of the feature class is valid, which means that you have a defined and well-defined coordinate reference system, and you have well-defined resolution and tolerance. We will see it in the next slide. If they aren't set incorrectly, so you have some spatial reference system, but it is a bad system. It's not the system in which you have the coordinates, or you have incorrect resolution tolerance settings, that you may experience performance degradation. So your process will run slower and not so fast than it is expected. Errors, maybe crashes, or incorrect results. So maybe you won't get any warning or error message or something, but the results will be incorrect. Feature class spatial reference become invalid, mainly if the data is imported from other non-RGS system, mainly if you are using S3 shapefile, or if you are importing from different file formats. So the incorrect or invalid spatial reference means or can it can be an incorrect coordinate reference system definition, incorrect X and Y resolution, which is the minimum distance in map units, for example, meter, that separates unique X and Y coordinates. And I want to show you these figures here to understand the resolution and the tolerance. So the resolution here is the minimum distance of two distinct coordinate values. So if you have coordinate values between this range, the values will be, you can say, rounded or truncated into maybe it's truncated into one digits or the digits after the resolution defined. So the default value of the resolution is 100 of 0.01. And for the tolerance, what is tolerance? The tolerance is the minimum distance between coordinates. And if you have two coordinates inside this distance, inside this tolerance, the software will see them or look at them as they were one coordinates or 1 points. So it will merge them, and the software can is allowed to move the points, the coordinates inside this tolerance, you can say, square. And the default value is 0.001 in the map units, of course. So the invalid reference, spatial reference means invalid or incorrect coordinate reference system definition, or incorrect resolution tolerance values. Okay, before jumping to the invalid geometry, I want to show you a small example of invalid spatial reference systems. I change my share. Now you can folder with S3 shapefiles. Maybe it's too small or tiny. Doesn't matter. Not the Jamaican, but for example, these fire stations. This is a shapefile format with several files, as you know, the SHP, DBF, SHX files, and additional files. And as you know, the PRG file here, the same name, but with PRG extension, will store the spatial reference information. It is a well-known format, description of the spatial reference system in a well-known format. And I will rename this project file. I want to delete, but I will rename and add this shapefile to my map in QGIS. Just a moment. Okay. First of all, you can see a question mark here next to the layer, which will warn us that there isn't any coordinate reference system set to this layer yet. And in this case, if you zoom to the layer, the points will be everywhere in Africa, somewhere in Benin, maybe. I don't know the country. So it is here everywhere because the coordinates stored in this fire stations shape file, spatial data set, are in, we know it is in Jamaican grid, but the software don't know that, doesn't know that. So it thinks it is the same coordinate reference system as the whole map, the project, we can say. It is the coordinate reference system of this base map. It is a web Mercator projection, doesn't matter. So the problem is that our points are on a wrong location. So we have to define the coordinate system for this layer. Sorry, and this is the Jamaican grid. Say add, and now it is disappeared from this location, and I can zoom to the layer extent, and now they are on the right position in Jamaica. So if we have invalid or undefined spatial reference, for example, coordinate reference system, the software GIS cannot manage the data set. It will put on wrong location, or if you are doing some processing using this data, the results will also incorrect. For example, if you want to select or the points in one of your counties or region, it won't result anything because the points are without a valid spatial reference system everywhere in Africa. So there won't be any overlap between your county polygons and the points. Okay, now let's go back. We will see similar examples on the practical workshop. Let's go back to the slides and talk about shortly the invalid geometry. What is an invalid geometry? Why it is a problem in the GIS, and how can we fix and repair them? In a GIS application, sorry, a GIS application is built with an assumption that the features geometry follow certain specifications, which means they have valid geometry. And if you are working or processing data that does not follow a specification, it can cause poor performance, similar to the invalid spatial reference, or can generate errors, crashes, or the operation may succeed without any apparent problem, but the results will be incorrect, and you want to understand the reason behind. So there are some examples here of invalid geometry. They are polygons. For example, unclosed polygons, which means the first and the last nodes on the boundary are not on the same location, which is this unclosed polygon, or the order the polygon of the vertices along the outer boundary or it is also called exterior ring is incorrect, because by default, based on the standard specification, there is a fixed order of the vertices along the exterior ring, which is a counterclockwise direction or order. In the interior rings, if you have horse or islands, yes, horse maybe inside the polygons, the order of the vertices has to be in the clockwise. Sorry, I don't know how to show you because I am mirrored in the webcam, I think, but you can see on the image the figure. Or it's also an invalid geometry if this inner and exterior interior and exterior rings crosses each other. It's a very it's very often we can meet very often geometry like this if you are digitizing something and accidentally you put the vertices on wrong location, then you will get strange intersections inside a polygon. We can have duplicated nodes, for example. Two nodes have the same coordinates, or if you have less than 3 nodes, we cannot define or talk about the polygon again, of course. So different types of invalid geometry exists. We have to find them and we have to repair them. One of the most common source of these type of errors, these type of invalid geometry, are the shapefile formats, because it is implemented in several softwares, as you know. It is you can use it in commercial softwares and open source softwares as well. And if this implementation is wrong or there is some errors in the implementation, then the software will create invalid geometries. And if you want to use it in, for example, in ArcGIS, before you perform any geoprocessing, you have to check the geometry. You have to check for invalid geometries and fix them. Okay, there are two tools in ArcGIS to find and repair these invalid geometries. One of them is the check geometry to find them, and the other is the repair geometry. The check geometry will generate a report of all features with the geometry problems. Of course, you have to define the standard you want to use to validate the geometry, and yes, and the errors you can manage by manual editing the geometry or by using this repair geometry tool. Here you can see the list of available geometry errors, which mean results in invalid geometries. I won't talk about more detail. These are also from the ArcGIS help. We will try the tool in the practice later. So if you have the errors, the problematic features, we can fix them manually, edit them manually, or we can run or perform this repair geometry process. And here you can see the solution of the given errors. For example, if you have a duplicated vertex along polygon boundary, for example, then one of the vertices will be deleted. It's a very simple fixing method or method. Okay, And as a last part of this workshop, we will talk about an extension of ArcGIS. In the practice, it will be on the advanced user on the third practical workshop. I think it's a very interesting and a very useful tool or tool set which can be used to check the data quality, because it will check the data quality. It will look for errors in the geometry and in the attributes as well. So this is the data reviewer extensions. As I know, you have these extensions. You are licensed for these extensions, so we can use it in Kingston in the practical workshop. So this data reviewer extension provides a system for automating and simplifying the data quality control. So there are many predefined can say workflows to find the errors and to correct them automatically or semi-automatically as well. This quality control methodology or tools allow an efficient and consistent data review process. It will create reports as well from the errors. It can be an automated and semi-automated analysis, which will, as I mentioned, detect the errors in the feature integrity, the attribution, the spatial relationship with other features, like checking the topology relations as well. The detected errors will be stored, then can be listed, reviewed, and corrected one by one. And we can also create a report from the identified problems or errors. A life cycle of errors look like this. So first of all, we have to find and record the error. In this next step, we have to perform an editing. It can be an automated step as well, or make an exception. And in the last step, you can modify the status of this error. It can be an accepted or an unaccepted error, or that it is managed. The automated data review evaluates the feature quality without any human intervention, and it does not require the specialized programming skills. You have to use only the graphical user interface of the software of ArcGIS. Of course, you have options to configure these checks. And the configuration of the checks are based on the quality requirements we talked about earlier, and I think I also paste the same figure here again. We will check it soon. So these automated review will do everything without human intervention. Of course, before that you can customize the checks. This quality assessment, this checking process can be achieved during the feature creation. So as you digitize, for example, geometries and features and store attributes as well, in the editing session, it's good. It's a good option because you can reduce the need for rework. You don't have to work after and again the feature, or you can also check your already existing features, of course, and find the different problems, errors. As I mentioned, there is a semi-automated options or data reviews, which needs, of course, human interaction, but they are guided workflows. For example, identify missing or misplaced or miscoded features. You have to review visually, manually the features, but you can jump from feature to feature very easy, and it can be very effective way to correct, to fix these errors. So we we have so-called data checks, which are automated validation of a specific condition based on predefined configuration against one or more features or relation of features. It will assess the data quality, accuracy, completeness, logical consistency we talked about earlier. The data constraints will automated methods that detect the features or the attributes or the problems or issues with the features and attributes and the relationships already during the editing session. So as you create the feature, so if the newly created or the feature you want to create don't meet the requirements, the data quality requirements, for example, you don't want to allow drawing lines shorter than, I don't know, 5 centimeters in a network, it doesn't matter. It won't create new features if the vertices are, or the nodes, or the end and the final nodes, starting the end nodes, or the whole length of the line is shorter than this threshold value. These are the data constraints we are working during the editing workflow. That's the point. And the data checks can be done after you created the features. So we have to define these rules, these reviewer rules, and it will store in the geodatabase along with the features you want to validate. And then as you get the result, which is a table with the rows, and or in these rows, I will show you some screenshots soon. All the errors will have an ID, will identify the features, which is participating in this error or problem or issue, and provides information about the condition or the severity of this problem or error, and the status, or it is already resolved or fixed or not. So this is the figure we already saw today, that the data quality requirements is based on different it's coming from different sources, the requirements of the clients, of different standards, and so on. So this is the basis of the definition of your reviewer rules as well. Okay, maybe it's not so important, but the logic, how to create, how to build up this workflow, this data reviewer workflow. First of all, you have to correlate your requirements to the capabilities in ArcGIS. You can have so-called functional requirements and data requirements. For example, just some example from this long list. It's also coming from the ArcGIS documentation. For example, you have to identify, it's 11, ID 11, to identify the parcel that don't have, that haven't overlapped by building footprint. So parcels without buildings. So this is a requirement, and there is a tool, there is a capability in ArcGIS, which will says this, which will check this relationship, and if it is a parser, if it can identify a parser without building, then you will mark it as an error. Or you can have a requirement that you want to have a report at the end of this review process. And there is a function in this extension which will create a report from all the errors, the identified errors, and your activity as well, that you fixed it or you make an exception, and so on. Okay, there are different, so all these checks can be categorized into spatial relationship checks, attribute checks, and feature integrity checks. And the spatial relationship checks will, of course, analyze the spatial relationships between the features. For example, are there any overlap between the polygons or gaps, or they are touching themselves or intersect themselves in specified distance or not. We will see some examples in the following slides. The attribute checks will analyze the attribute values stored in the attribute table. For example, one attribute value is dependent on another of the same feature. For example, I don't know, you have attribute A and attribute B, and attribute B has to be 2 times of attribute A. So if it is, it's from some reason the attribute B is another number, for example, 3 times of attribute B, then it will marked as an error. Or if you have a list of street names in your city, you can in a table, in a standalone table, for example, you can check if there are any other street name in the street feature class outside from this list. So if you have a mistyped street name in your database, you can find that in this way. Feature integrity checks will analyze the properties of the features, like the vertices, how close are the vertices inside one feature along the polygon boundary, for example, or are there multiply parts of the feature when it isn't allowed, for example, and so on. These are also the list of different attribute checks. Some of them we will try in the practical workshop. For example, you can, if we are talking about attribute check, we can check if the attribute values are in the predefined domain. So if we create a domain for the number of lanes of the roads, it can be 2 and 4, for example, and we have an attribute for the number of lane, for example, 3 or 1, that it will be marked as an error, of course, and we have to fix them. As I mentioned, this table-to-table attribute, we can find values which cannot list in another table. There are different geometry checks which will check the integrity of a feature, not the relationship between feature, but inside a feature. Is it a valid geometry we talked about earlier? Is there any cutbacks when the angle between two connected line segments is too small, or are there duplicated vertices, or the number of vertices is, or the minimum number of vertices is, or the maximum number of vertices were predefined, and the feature has more or less vertices than that threshold. There are different polygon checks, like the overlap and the gaps, or unclosed polygon, invalid geometries. You can have checks for polylines. So for different geometry types, you can have different type of checks. Like you can find these dangle nodes, or unnecessary nodes, these so-called pseudo nodes. And there are the relationship checks, if a feature is inside other features. All building footprints are inside parcel polygon or not. Yes, and here in the, doesn't mention here in the last column, you can see the workflow where these checks can be applied. For example, this feature-on-feature checks can be used as a constraint. So as you digitizing, as you creating the feature, for example, you want to draw a polygon footprint, building footprint outside of parcel polygon. The system won't allow you to do that, to finalize that geometry. And the validation workflow means that you can perform these checks on already on existing features or feature classes. And as one of the last slides, some screenshots from the software. Here you can see predefined checks for polyline geometries, for polyline features. You have to select one of the checks. It can be a constraint, so you can use it in the editing session, or it can be a validation after the editing, or for existing features. And you select a check, and you have to customize these check. For example, in this case, we select must not exist with 1 foot from each other. So sorry, it was the geometry. I don't know, one of the validation checks, I think. Okay, it will check the distance between the root vertices. So it won't allow as a constraint during the editing, during the creation of a road segment. So it won't be allowed to create 2 vertices in 1 foot distance, inside 1 foot. But of course, you can customize all the parameters, for example, these tolerance values and so on. And you can add a name, a description, and so on, a severity of the check. And after you validate, after the software check all your features, you will get the results in the table, and you can manage them. You can fix them, or you can make an exception if it is not an error. Okay, and this is the last slide. It is an invitation for the practical workshop on the 29th of February. Will be 2 different workshops in Jamaica, one in the morning and one in the afternoon. The second practical workshop will be on the morning. It is for intermediate students. Here you can see the planned topic. We will work in ArcGIS Pro. It will be the platform. And we will see how to deal with how to manage metadata in ArcGIS Pro, how to update the map metadata, how to update the metadata of your spatial data set. And we will also use the Jamaican metadata template or standard, of course, and we use the data sets from the national data repository in the first part. And in the second part, we will create topology in GIS using, I think, parcels or these administration units or the street network, and try to find errors, inconsistencies in the data set. It will be in the morning, and in the afternoon, the workshop, the target group of the workshop are the advanced users, and then we will work with this data reviewer extension, and we try to work with different checks, constraints, and validations as well. So this is the plan of the practical workshops for intermediate and advanced users. Okay, thank you very much for your attention. If you have any question, we ask you to type it in the chat box. We will collect them and answer you in text, not now, but later. And if you didn't type your name and the organization yet in the chat box, please do that also. Thank you very much.